So we've learned various techniques of integration. Now we're just going to talk about integration strategies for a few minutes, because down the road when you see an integral, it's not going to be in the partial fraction section or in the trig subsection. It's just going to be an integral. So how do you go about evaluating this integral? So with the methods of integration, we basically have learned some analytical methods, and these various integration techniques that we've learned, like substitution, integration by parts, partial fractions, and so forth, are one way to do this, or using integral tables would be another way. Now we also could then, if we're not going to use analytical methods, we could use computer methods. So we use a computer algebra system, and there's two ways we can do this. We can use symbolic methods, or we can use numerical methods, which would give us an approximate, and these would be for things that maybe we couldn't integrate with analytical methods. So let's go through some sort of clues or ideas or things to look for so we know what to try. So one of the things we want to do is simplify the integrand if we can. So if we see something like this, it can look fairly complex, but really if I just get rid of the parentheses here, and I'm going to also rewrite this as an exponent, and so this one would be x to the 1/2 plus square root of x times square root of x is just x dx. Be very easy to integrate, so this would be x to the 1 higher power, which is 3/2, and then we need the reciprocal of that power, plus this one would be 1/2 x squared plus our constant of integration. So by simplifying that integrand, that makes it very easy. So let's look at another example. This may look fairly complicated, but if we will see what we can do to simplify this, this is sine theta over cosine theta, and then 1 over cosine squared theta d theta. So when I flip this over, I can go ahead and make this a cosine squared theta over 1, and then cancel one of these cosine thetas. And so that just leaves me the integral of sine theta cosine theta d theta. And then this one will be easy to do if I let u equal sine theta, and du then is cosine theta d theta. So we can see that this one is the derivative of this. So you can go ahead and do the u substitution, or maybe on these simpler ones, when you start to see those, you can almost do them in your head without the u substitution. But let's go ahead. This would be just simply u du. So this would be 1/2 u squared plus a constant, and then resubstituting, getting it back in terms of our trig functions, we've got 1/2 sine squared theta plus a constant. So by simplifying the integrand makes it pretty easy to work. Let's look at one more example. So as I'm looking at this one, if I will multiply this out, this will be sine squared x plus 2 sine x cosine x plus cosine squared x dx. And now this is going to simplify, because here's my favorite trig identity here. I've got sine squared plus cosine squared, and so that's just going to be a 1, and plus 2 sine x cosine x dx. Now I'm actually just back to something I just solved, because I just did this one. And so I've already got that. I can integrate the 1 and get x, and then this just has a constant out in front of 2. But on the last one that I did, it had a 1/2. So essentially, if I had that 2 out in front, that'd cancel with that 1/2. So it's just going to be a sine squared theta. So this is just going to be sine squared x plus a constant. Another strategy is to look for an obvious substitution. If I see something like this, because I can see that the derivative of an x cubed would be an x squared term, then I can easily see what I would want to try for a substitution. Now I could use 3x cubed, or I could use x cubed. I think I'm going to go ahead and include the 3. And then du would be 9 x squared dx, and I can see that I have my x squared dx, so 1/9 du would be my x squared dx piece. So this is going to be the integral of, we'll put the 1/9 out in front, du, and then this is just going to be u minus 1. So we have 1/9 natural log u minus 1 plus a constant. Don't ever forget on these the chain rule, but the derivative here is 1, so we're good with that. And then getting it back in terms of x, I would have 1/9 natural log of 3x cubed minus 1 plus a constant. So looking for an obvious substitution would be, can you see some function and you can see that the derivative would be included there some way as well. Now the next thing we'd want to do is this, we're looking at the integrand, kind of classify it by the form that it is. So if we see trig functions, we see products of powers of sines and cosines, of tangents and secants, of cotangents and cosecants, then we know we can use substitutions because we know the derivatives in these pairs, the derivatives of sines or cosines, the derivatives of tangents involve secants, etc. If we see rational functions, then we would think partial fractions. We'd look to see if we could factor the denominator and split it up into partial fractions. We would look for integration by parts if we see the product of a power of x and maybe some transcendental function. Typically that's a nice integration by parts, and the tabular integration would work on those as well. Look for radicals, and if we see the radicals, we could try trig substitution if they're in the square root of some x squared plus or minus some a squared. Then we could think of draw the triangle and do a trig substitution. If we see some radical, some nth root, and we have this ax plus b, then if we use a substitution letting u equal that radical, a lot of times then we can use that technique of rationalizing. Then a sort of a next strategy would be to try again, because sometimes things aren't really obvious, and that's interesting here. If we think about it, if there's no substitution that's obvious, try inspiration, ingenuity, or even desperation. And sometimes trying some different things as you start to work it, you can see how that may do the trick. Also, often integration by parts doesn't have to be the product of the two functions, and sometimes it'll work on single functions. Example, when we had that integral of ln x dx, that didn't look like an integration by parts, but if we let u be ln x and dx be our dv, then the integration by parts worked. Sometimes we'll want to manipulate the integrand then by doing various algebraic things to that. We may want to complete the square. We may want to just try and write it in some kind of a different form so that then we could get it into something recognizable to integrate. And often relate it back to something that you have seen or worked previously. And sometimes we have to do more than one thing in the same problem. Maybe we do a partial fraction, and then after we get that done, we see we need to use a trig substitution. Then we need just a regular substitution. I mean, it could be more than one method involved in the same problem. If you watch the examples following this video, then we'll look at several types and just sort of talk about the strategy. Okay, this is what we see for the integral, so what would go through our head? And we'll talk about strategies as we solve some examples. One last question before we leave this. Can we integrate all continuous functions? Back when we learned the fundamental theorem of calculus, we learned that if we had this function continuous on this closed interval from a to b, then it was integrable. But can we integrate everything? Now we can look at several functions that we would not have a technique for integrating, and here are some examples. You could try various techniques that we've learned, but the actual analytical methods for integrating these, we don't have them. We do have the numerical, we have the computer algebra systems, but we can have functions like this and we can know that they are integrable. Actually, the majority of functions don't have elementary antiderivatives. Now, a lot of the functions that we need to work with are elementary functions that have elementary antiderivatives. Now, what do I mean by an elementary function? They're functions that are made up of polynomials, rational functions, power functions, exponentials, logs, trigs, inverse trig functions, hyperbolic, inverse hyperbolic functions, and they are obtained by using these functions by adding, subtracting, multiplying, dividing, or doing a composition of these functions. So we know that if we have these that are continuous, they are integrable. We just may not be able to explicitly write down the solution analytically.